Greetings, everyone. Welcome to the Kentucky Watershed Academy. This is Steve Evans with the Kentucky Water Resources Research Institute, and today we'll be talking about stream and floodplain restoration BMPs as part of Module 4, which is focusing on land use impacts and related best management practices. So to start, we want to consider why would someone conduct stream or floodplain restoration? Well, there's many different reasons for that. Some of those can deal with stream hydraulics and hydrology. Maybe there's extremes or flooding, or the channel goes dry and they want to restore a natural base flow. Maybe it's increasing the floodplain storage or changing the channel shape and profile. Other issues can deal with erosion or sedimentation. Perhaps the banks are eroding and need to be stabilized or protected, or there's aggradation in the creek, building up of sediment in the bottom of the stream. And finally, it may be just an increase in habitat. Adding riffles, pools, runs, and glides can provide unique places for the aquatic organisms to live. They can add vegetation, which provides shade benefits, and adding places like tree falls or root wads or leaf packs. You might recall from Module 2, we looked at how the varying depth, velocity regimes, and flows in the water provided ideal habitat to increase aquatic diversity. So this includes riffles, runs, and pools that can be colonized by different aquatic species. And so when seeking to design habitat enhancement structures, it's important to consider all of these in-stream components, as well as a healthy, well-vegetated riparian zone. Having different places where creatures can live, such as emergent vegetation or under rocks of different sizes, in root wads or in leaf packs hanging on the branches, woody debris, and other locations, all add important diverse niches that can increase the habitat. Different creatures use different habitats, so variety is good. When selecting habitat restoration BMPs, it's best to identify and address the underlying causes of the problem rather than simply applying BMPs that treat the symptoms. A land use change or direct disturbance to the stream channel can set off a chain of impacts to the stream's geomorphology and hydrology, its hydraulics, its functions, and its biological composition. So, for example, if a recent road project has channelized an upstream stream segment, then you may need to find ways to manage flow and your associated sediment runoff between the construction site and your habitat improvement site. Otherwise, efforts to restore habitat function will be futile. In addition to considering upstream activities, a combination of restoration techniques are typically needed to address prevailing conditions and desired goals. A single technique may become short-lived, ineffective fix on a larger system-wide program. Thus, individual restoration techniques should be integrated into a broader restoration plan. For most restoration efforts, a licensed engineer is necessary to approve the plans. This overview of BMPs is so that you can have an understanding of some of the underlying techniques that they use. There are certain steps that are typically taken in the restoration design process. The first step is planning the structures and the layout of the stream restoration. Man-made structures and quality existing habitats should be identified, and structures should be spaced so as to best enhance habitat diversity. Secondly, these structures should be sized appropriately in order to accommodate the full range of flows in the stream, from base flow conditions to out-of-bank and bankful conditions. Thirdly, the velocity and sediment discharge relationship should be examined so that deposition or additional erosion are not caused by the stream design. Barriers to flow conveyance should also be avoided. Lastly, the structure should be designed and installed giving preference to on-site materials such as logs, stone, and trees that can be reused on-site. There is an old saying that if you're failing to plan, you're planning and fail. Well, in stream restoration, you need to think about the implications of failure of your project, particularly if your project involves changing the channel slope or cross-section, as this can cause instability not only in the reach where the restoration activities are occurring, but upstream and downstream. It can also change the potential flood elevations, causing areas to flood that did not before. In some cases, certain BMPs are just not feasible where head cuts or degradation of the stream is occurring due to erosion. And further, A bank restoration activity may be thwarted if stream bank toe protection is not added. There are commonly permits that are in place to ensure that these types of failures are addressed, and professional design assistance is necessary in this process. So be sure to check those prior to starting a project. Habitat enhancements frequently accompany stream restoration practices. Although individual habitat enhancements, such as boulder placement or felled trees, can be placed in the stream, the best approach to improve habitat is to restore a fully functional, well-vegetated stream corridor with a well-managed watershed. Long-term habitat improvement should rely on natural fluvial processes interacting with a well-vegetated stream corridor and associated woody debris. For this reason, practices are installed in coordination with upstream watershed management efforts. Habitat and stream restoration objectives can be grouped into a number of ways, but for this presentation, we're going to be beginning at the outside of the stream and moving towards the channel. This will not be a comprehensive guide to all floodplain and stream restoration BMPs, but should orient to general practices and concepts. So beginning at the outside of the stream and working toward the center, we begin with the floodplain. And there's a variety of different best management practices that can be added to stream restoration to increase the flood storage as well as the habitat in the floodplain. Stream floodplains provide storage of floodwaters, but with development in the floodplain or increased imperviousness causing a higher peak flow, more area may be impacted by floods. In the picture, you can see the small area at the bottom was the floodplain before filling. After development, now a much wider area floods because the flood level is increased due to the narrowing of the channel. Now houses that were previously unaffected by floods are now liable to flood. In many cases, developers will install detention basins to reduce the peak flow into streams. However, another alternative is to require that the equivalent storage capacity is retained within the floodplain itself. Some communities require no net rise to the flood levels by requiring compensatory storage excavation offsets. So here you can see in the picture at the top, there's an area that's of the 100-year floodplain that's filled by construction. And so an equivalent area is removed on the right bank in order to offset. At the bottom picture, you can see a neighborhood that was built within the 100-year floodplain. And again, a little bit downstream, an area is excavated in order to offset this filled area. In areas in which development has already occurred and the stream bank has become channelized, that is, it no longer has access to its floodplain, additional flood capacity can be created by rolling back the banks of the stream and providing access to a new floodplain. This is also called a two-stage channel design because it has a small channel for the lower base flows and a wider upper channel with a floodplain bench. This improves the habitat as well as the sediment transport capacity. At the bottom picture, you can see this is a common two-stage agricultural ditch design, but the same holds true in urban areas, which you can see a floodplain, the stream is moved away from the housing, and you can add some habitat there as well. We've seen how increasing the floodplain can provide additional storage and reduce the impacts of flooding on infrastructure surrounding the stream. But another benefit is that as water spread out across that floodplain, they begin to slow down, and it reduces that erosive force within the channel. And so a simple concept of stream restoration is to increase the sinuosity of a stream. A straight stream is going to have more erosive force, but as you add bends, it will begin to slow down those waters. That's led some to have a philosophy of stream restoration that just focuses on having a wide floodplain and allowing the stream channel to find its way across this floodplain, maybe in a braided stream or in an anastomosing stream where there are many different channels that occur over this reach. This can provide a number of habitats and again It allows for a minimal erosive force over the channel. Operating on a similar concept to the multiple channel model is the addition of floodplain, streamside, bankful, or benchful wetlands. These are all different names for the same thing, a floodplain wetland. And these provide habitat, storage, and just a place to slow water down. So as the water comes over its banks, it can enter into these floodplain wetlands where the bacteria begin to work on that and provide treatment for nutrients or other pollution sources. So ideal candidates for the creation of these floodplain wetlands include large, low-lying swaths of lands adjacent to the channel, particularly if they're publicly owned. That will increase the feasibility. Another practice that is often installed in floodplains is a groundwater dam or groundwater berm. These are often used in conjunction with a multiple channeled stream or a floodplain wetland, but they can also be used with single channel streams. The idea is that excavation is conducted all the way down to the bedrock. You can see that occurring in the top right picture. This is then filled with a layer of clay that the water cannot penetrate through, and therefore it must flow over the top of it. Typically, these are done in an area where a riffle is located. This raises the groundwater level and allows for a more sustained stream flow. Oftentimes during channelization, that base flow is lost, and so a groundwater berm can be used to restore that. Finally, if we're talking about the addition of habitat within the floodplain, microtopography is very important to allow for a variety of habitats that are there. Under a natural channel formation, sometimes meanders are cut off and they form small lakes and levees that can create wetlands. So across these floodplain wetlands, hummock and hollow patterns can create this bumpy surface, which causes a lot of different habitats and elevations. As water fluctuates upwards and downwards over the area, they may support different vegetation, and therefore different type of aquatic organisms can live in these habitats. Some restoration efforts will also include simulated tree falls, where wood is left in place with scoops removed by a backhoe on the back end to kind of simulate some of these unique habitats that occur, this micro topography that is added in a floodplain. As we move from the floodplain more towards the stream channel, we come to the riparian zone. And you can't have a presentation on stream restoration without mentioning riparian restoration. It's very important. This is the area where volunteers can make a difference and where your engineering plans are not required. Riparian restoration can be done through conservation easement. It can be done through buffer setbacks. It can be done through greenways. It can be done just through native planting and invasive removal there. But in all of these areas, they add habitat for different organisms. They also add shading to the stream. They add filtration of pollutants on overland sheet flow. So riparian restoration is very important in overall stream restoration. As we move away from the riparian area, we come to one of the most common area for general issues that need to be addressed in watershed improvement efforts, and that's stream bank stabilization. This is using different practices in order to prevent or to slow soil erosion from the edges of that stream channel. This can be done through armoring, using rock or concrete, using vegetative methods, trees or logs, or indirect methods, taking the flow and moving away from a bank. But all of these are designed to put protection there such that the force of the waters that are hitting that bank are matched by some type of protection that's equal to that force, and therefore it's protected. One of the most common bank stabilization techniques is the use of riprap, and perhaps the overuse of riprap. In this case, Appropriately sized stones extend from the toe of the slope to whatever the height is needed to provide that long-term stabilization and durability. And that's when it's used, when you really need a long-term solution, when the discharge is very high and provides a threat to proper properties, and there's no real practical way to incorporate vegetations. This should be used with vegetative plantings in order to stabilize the upper bank areas. But again, when you use this technique, you may have stable banks, but you don't really have any habitat or water quality benefits that are added by the riprap. Another technique that's a little bit better than the riprap in some cases is the use of gabion baskets. These take those similar stones and they are enmeshed in wire rectangular baskets that help form the structures on the wall. And I say these are a little bit better because they can provide, you can introduce live branch cuttings in place and allow them to take root, and that allows some habitat, not very good habitat, but some habitat benefit in these structures. Sticking with our use of rock here, we come to the stream bank toe support. So in this restoration technique, the quarried rocks are just placed along the toe, that very bottom of the channel, in order to provide some additional support and armoring that's there. These are in places where vegetation cannot be used, and the bank may be beginning to be undermined there. This is a lesser use than other techniques, so you're just stabilizing that bottom area and then using the upper bank vegetative techniques are used in that area. Moving away from the rock-based stabilization techniques, we come to coir logs or fiber rolls. These are two-shaped erosion control devices filled with a variety of materials such as straw, coconut fiber, or composted materials. Each roll is then wrapped with a netting like burlap or coir to provide longevity. These rolls or logs are staked into the bank and allowed for the rooting of plants or live stake trees to grow over the surface. When installed in combination with straw mulch, erosion control blankets, these can be used to armor even steep slopes while providing habitat. Coir logs or fiber rolls also help to slow, filter, and spread out overland flows. And so this helps prevent erosion and minimizes the rill and gully development. They can also help to reduce the sediment loads to receiving waters by filtering out that runoff and capturing the sediment. Another bank restoration techniques is the addition of root wads. Logs with root wads at the end of them are simply placed in or on the stream banks. This helps to prevent erosion, trap sediment, and improve the habitat diversity. These should be placed in the outer meander bins and other areas that have concentrated flow velocities on the banks. These areas can tend to be undercut a little bit, and they form an area of deep water with shade, and this is great habitat for a variety of different fish species. Also, these root wads, as they branch out into the stream, tend to collect different organic debris and form leaf packets. And this is a great food source for many different macroinvertebrate species. So you can see in the diagram that we have here, there's a footer log that's placed to kind of armor that toe of the bank. That root wad is placed up through, so it's perpendicular to the stream. That's anchored by some large boulders, and then vegetation is allowed to grow on the soil that's placed over the top of it. Another bank restoration technique that's maybe a little bit more greener than the concrete or rock armoring is the use of engineered log jams or crib walls. So log jams we see on the top picture is a crisscross pattern of logs that are actually anchored into the stream bank through their interlocking pattern and the use of rebar. This provides stabilization as well as a variety of habitat there within the branches. Crib walls are like retaining walls, but they're just made up of logs, which will cover over with vegetation over time after their decay. So it provides a very long-term stabilization. Another restoration technique that can be used is a tree revetment or snags. The idea here is to provide arming of the bank to allow for healing from the restoration and growing over with a more permanent vegetation. A tree revetment is an inexpensive way of stopping erosion by anchoring trees together along a stream bank. The trees greatly slow the current along the eroding bank, which decreases the erosion and allows the silt to be deposited along the bank and within the tree branches. The deposited material then becomes a good seed bed in which river trees such as sycamores can sprout and grow. The resulting trees spread roots throughout the revetment of the stream bank, and then by the time that these trees have decayed, the bank should be stabilized by the roots of the living trees. As an added benefit, these provide a lot of excellent fish and wildlife cover, so additional habitat while that process is occurring. Another bank protection technique that may be utilized in conjunction with other techniques is live staking or brush mattresses. These work best in areas with light erosion or in areas of more severe erosion when used in conjunction with other practices. To install live stakes, straight branches of living woody plants like willows or dogwoods are driven into dirt either by hand or with a dibble bar. The cuttings are made from plants that will sprout roots and grow from these branches. The stakes should be snugly planted, about 70% buried and 30% exposed. Place the stakes in a triangular pattern about 2 to 3 feet apart and with a maximum of about 4 stakes per yard. Typically this is best to do in the early spring or in the late winter. They can be planted deep enough to access the soil moisture and eliminate the need for irrigation. Here we see a picture of that in the top right. Geotextile fabric is often laid down first in order to hold off further erosion until the live stakes begin to grow. The fabric is anchored by burying it underneath the substrate behind the live stakes. And then oftentimes riprap can be added at the toe to provide some additional stabilization. Brush mattresses are a little different variation of live staking. They're installed perpendicular to the stream in a shallow trench and then staked down. And these brush mattresses are just a combination of live stakes as well as other brush cuttings and then live bundles of wood called fascines. The cost of this is low. It's easy and it can be done by a landowner. It can be pretty effective. One of the difficulties though is locating a source of the live material in order to generate the woody cuttings. Having addressed some of the techniques for bank stabilization, we come to our final piece in this presentation, which looks at the in-stream structures to address the profile and cross-section of the stream channel. Land uses involving the installation of culverts, straightening of channels, and removal of riparian vegetation can all cause damaging changes in the channel slope. Usually we see in side channels from bed erosion, that is degradation, but a raised bed, aggradation, can also result with no pool or riffle sequences and a shallow or wide channel or with a silty bed. If a stable channel is required for habitat design, then grade control structures should be considered as the very first step in the design process. We'll look at a number of examples of these controls, but in general, they're designed as a U or V shaped to create downstream scour pools for fish habitat or resting. If properly applied, these structures can be very effective. Sometimes, however, their effectiveness can be lessened by unforeseen changes in the channel, as the stream might meander around the structures, or they can be destroyed by excessive flows or even catch too much gravel. Log structures will also eventually decompose. And therefore, some designers will just try to stabilize the floodplain and allow for flexibility in the formation of the channel over time. The first of the structures that we want to consider is the step pool sequence. Step pools get their name because from their profile, they sort of look like a series of stairs. They consist of a series of structures designed to dissipate energy in a steep gradient section of the stream. They're often used in areas where head cuts are migrating upstream or the channel has degraded below a culvert or outfall. So as a step pull, rather than wiggling the stream back and forth to slow it down, you move it up and down in a cascading fashion. So step pulls are made of large rock alternating in short, steep drops, which form pools, and then longer areas where the flow will be directed at a low gradient or even slightly uphill. The number of steps is determined by the extent of the drop in the elevation of the stream. The requirement is that the structure has to be stable at all flows, and the rock must be large enough so that it is essentially immobile. The drops must also be low enough to allow for aquatic life to migrate upstream. Another in-stream structure is the rock weir. Weirs can be made from logs as well as boulder or stone structures, but they're placed across the stream channel in order to serve as a grade control to provide a variety of velocities while maintaining the bed load transportation in the stream. So in this picture, you see that the water is flowing from the left side of the stream to the right side. So weirs point upstream with the sides angled out to about 15 to 30 degrees. The legs of the weir will actually continue upstream into the stream bank just above the bank full elevation. The stones that make up the weir do not actually touch each other, and so that way in base flow conditions, the water is forced to flow around and between the stones. Whereas during high flow, the water rises over the stones, creating a scour pool below the structure, but allowing sediments to move through. Uh, Again, these weirs can be constructed from logs, um, and like rock weirs, log weirs provide bed form diversity, maintain the channel profile, and provide pool and cover habitat. The cross vein structure is similar to a weir, but differs in that the stones do not extend much above the stream base flow level. The cross vein decreases near bank shear stress, velocity, and stream power while increasing the energy in the center of the channel. Essentially, you can see the flow in the picture there as from the top left to the bottom right, and so it's in a U-shaped upstream structure. Often cross veins will be placed above or below a meander to establish elevations for pool and riffle formation. Many fish species use these pools as areas of refuge because of the increased water depth that forms below them, and they're prime feeding areas for items washed into the pool from the riffles. J-hook veins can be constructed of logs or rocks or both of them, but they're used to reduce erosion along the bank by redirecting the flow into the center of a stream. In this picture, you can see that the flow is going from the top to the bottom. And so this J-hook mimics the effect of a tree fallen partially into the stream. They should be carefully placed to avoid scour erosion on the upstream side from the eddying effects of the water. The curved end is placed to encourage a downstream scour pool formation. The structures can enhance habitat by creating downstream scour pools, narrowing and deepening the baseflow channel, enhancing riffle habitat on the upstream side. The boulders also tend to trap leaf packs and small woody debris that are often used as a food source for macroinvertebrate species. Flow deflection can be achieved through the placement of either log or stone or a combination of the two, known as wing deflectors. In the picture on the slide, we see the log form of this with the flow moving from right to left. Wing deflectors protrude from the stream bank and extend partially across the channel width. They are usually simple to construct and a cost-effective way to restore a meandering thalweg to alter channels that are wide, shallow, and sluggish. These structures are meant to behave as an artificial bar, reducing stress on the banks by directing flows towards the thalweg, the area of the lowest bed elevation in the stream. They enhance habitat by creating scour pools. They can be installed as single structures or in an alternating series or opposite each other in what's known as a double wing deflector. Deflectors placed in sand streams may settle out or fail due to erosions, so they should not be recommended in those areas. Here we can see two wing deflectors used together, or what's known as a double wing deflector, in which the flow is moved away from the banks of the stream and towards the center, creating a scour pool there. In the diagram on the left, we can see this is done with rocks, and the diagram on the right, an engineered log jam is utilized. Logs can be utilized in a number of ways for grade control. In a log drop, as seen in the top picture, a log is placed perpendicularly across the stream and buried under several feet of the stream bank on each side. In some cases, a second log may be placed on top of the first log, depending on the base flow elevation. In some cases, notches can also be made in logs to concentrate base flow in the center. Care must be taken as to the elevation for the logs, as they may form a barrier for fish passage if too high. As an alternative to the log drop is the V-log structure, in which two logs form a V pointing upstream. The logs are lowest in the center and raise in elevation as you approach the stream banks. This structure has the advantage of not potentially creating a fish barrier and is more effective at concentrating flows and creating scour pools below the structure. Another in-stream structure that is associated with the bank but requires more extensive construction is a lunker. Lunker is a crib-like wooden structure installed along the toe of a stream bank in order to create overhead bank cover and resting areas for fish. It consists of two logs with wooden spacers inserted between them. Additional logs are also nailed across the spaces perpendicular, and so a structure is formed. This structure is installed by first grading the stream bank back and then creating a trench along the new bank line. This trench must be wide and deep enough so that the lunkers lay flat and are completely covered by water. The lunkers are secured to the stream bottoms with rebar, and once in place, rock is placed on top and behind the lunkers, and the stream bank is graded down to meet the front edge of the lunker. Again, these provide excellent habitat for fish and mimic undercut banks, but still have structural stability. Another structure that we want to touch on is an area that's out of sight, but it's very beneficial for water quality, and that's the hyporheic zone. The hyporheic zone is simply the saturated area underneath and adjacent to the stream where the groundwater connects with the surface of water. And the addition of wood chips and to gravels in the zone can help with natural processing, particularly with denitrification, so the removal of nitrogen from the stream. It can also provide some unique habitat, some microbes and aquatic organisms. Another stream restoration technique that is commonly utilized is the removal of check dams or lock and dam structures. Dams were once frequently installed to provide power, flood control, irrigation, and recreation. However, these dam structures altered the hydrology of the stream, creating an often slow-moving impoundment. These dams cause sediments to slow down and accumulate, burying stream bottom habitat. They can also affect riffle habitats in the surrounding areas. Removing these dams can restore ecological flows, which can support a variety of fish and wildlife, including mussels. This also allows for improved natural transport of sediment and nutrients. And finally, it can eliminate a potential safety hazard as these structures approach failure. In this presentation, we've covered some of the many stream restoration practices that may be utilized by water resource engineers. It is important that you have a general idea of the types of practices that can be implemented for planning purposes and to think of requests, but in most cases, the designs will need to be conducted by registered engineers and hired contractors. We hope this overview provides some understanding of how streams may be improved in your watershed.